Hi everyone, and welcome to another seminar of Mathematics and High Energy Physics, Physics Latam. Today we are happy to have Mahan Mj with a talk about dimensions 1, 2, 3, 4, and higher dimensions. Professor Mahan is Dean and a faculty member at School of Mathematics, TIFR Mumbai. He completed his PhD from UC Berkeley in '97. He is also recipient of the 2011 Shanti Eswaru Bhatnagar Award in Mathematical Science, and in 2050, the IFOS Prize for Mathematical Science. He is best known for his work in geometric group theory, Kleinian group and hyperbolic geometry, probabilistic geometry, surface group representation, and vector bundles, Kähler groups, and topology of algebraic variety. His most notable work is the proof of the existence of Cannon Thurston maps. This led to the resolution of the conjecture that connected limit sets of finally generated Kleinian groups are locally connected. He is also the author of the book titled Maps on Boundaries of Hyperbolic Metric Spaces. So we are very happy to have him with us today. I hope you all enjoyed his talk. Now I leave you with him.
Okay, thank you very much, Daniel, and it's a real pleasure to be here virtually. So what I'll do is this. So this talk is split into two parts. The first part will be a general introduction to topology, where I'll focus on low dimensions, and we'll see that this is something that we see all around us. That's going to be the first half of the talk, and it was going to end with some general facts and history of something that has happened in three-dimensional manifolds, exciting developments. And so the second half of the talk, I will take a short 5-minute break maybe after this first half. And the second half of the talk is going to be basically on three manifolds per se. Okay, so now let's start with the talk. And the first point that I want to make is that geometry in dimension 1 is something that all of us are familiar with from childhood. So here you have some children's pictures, children's games, where children take sticks and they arrange them together in geometric patterns. Yeah? So you have various patterns here. I mean, this is not supposed to be an advertisement of any particular brand of children's games, but we are just trying to illustrate that, yeah, that even naively, when we are children, we play around with these, and what we are really doing is one-dimensional geometry. Where one dimension, the dimension 1 is basically the dimension of a stick here. Yeah? All right. And this is not just children's drawings from today, but it's something that is part of our heritage as a species. So there is a little island called Vanuatu. It's one of the French islands. There's an ancient form of sand art, and they're called sand drawings. Sand drawings not spelt in the usual way of sand drawing, but they're essentially spelled as SANDROINGS. Yeah, so essentially this is the local indigenous people. They make these patterns on the ground, where the policy is the idea is to make these diagrams without raising your finger from the sand. Yeah. So this has been declared, I think, some 10 years, 12 years back by the UNESCO as part of the oral and intangible cultural heritage of humanity. And this appeared a few months back in the November 23 Scientific American as this one-dimensional geometric figures. And it's we'll see that the formal part of it really starts with Euler, but let me just try to minimize this a little bit. Yeah.
Yeah,
Okay.
don't worry. We cannot see that part.
You can see the right hand side picture. Is that all right?
Yes,
or?
yes, yes, yes.
Is it okay? Yeah. All right. So maybe I'll do that. Okay. So so UNESCO classified these sand drawings, and they are quite old, more than, I mean, older than the place where formally topology started, with probably Euler. And so it's, what I'm trying to say here is essentially that instinctively, many of us, I mean, all of us as members of a species, do something which is topology without really casting it into a formal structure. So the first part of the talk, what we'll try to do is, how do we try to understand from children's figures to these sand drawings, what is the common pattern behind all these figures? And the way we'll do this is by trying to pose some basic questions and try to see how patterns emerge as we proceed. Okay, so let's start with this. So now we are thinking of these one-dimensional drawings, and we are trying to cast them into some kind of a formal structure. So let's think of matchstick figures. Yeah. So basically, think of these black lines as the body of the matchstick, and the red blobs that are drawn in this figure as the match heads. So let's we draw these figures on the plane, and then we start doing some count. So this is, I mean, essentially there's this statement by V.I. Arnold, famous Russian mathematician, who described mathematics as the field of science or field of physics where experiments are cheapest. So this is supposed to be an experiment that we are doing, really, and we are trying to get some data out of it. Okay, so let's do that. So here we have a matchstick figure. What is the number of match heads that are there? So basically, how many red blobs are there? So you have 4 on the outer rim, 4 next, and then 1 more. So the total number of match heads is 9. The number of sticks is again 4 and 8, 12, and 4, 16. So that's, so the number of, yeah, so that's the number of match sticks. And finally, the number of regions inside is 1, 2, 3, 4, and another 4. That's 8. So match heads 9, match sticks 16, regions, white regions is 8. Okay. So we have just counted some of the basic geometric figures of this. And what we are going to try to do is see whether there is some pattern that emerges in all these figures. So here's, so after some playing around, this number of match heads minus number of matchsticks plus number of regions gives you the simple number 1. So 9 minus 16 plus 8, that's 1. Okay. And so keep this in mind. Number of 0. So these blobs are essentially what mathematicians call 0 cells or vertices. Number of edges, or these sticks, or number of 1 cells. That's the second number, 16. And the number of regions, which are basically 2-dimensional regions. So number of 0-dimensional regions, points, minus number of 1-dimensional regions, this is sticks, plus number of 2-dimensional regions. That's equal to 1 for this particular matchstick figure. So some simple thing emerges by playing around. And then we ask whether this is a pattern that's specific to this figure, or whether it's something that goes on and replicates itself. So we take another matchstick figure. This is, if you recognize it, it's basically something that it's a graph which represents the dodecahedron. So here again, how many match heads are there? So on the outer rim, there are 5. On the next, there are 10. And on the innermost, there are another 5. So 5 and 10, 15, and 5, 20. How many sticks are there? 5 on the outer. Then there are these 5 that come in from there. 5 and 5, 10. The next level, there are 10. So 10 and 10, 20. The next level, there are 5. And the innermost, there are 5 again. So the total number of sticks is 5 plus 5 plus 10 plus 5 plus 5. So that's 30. How about number of regions? Again, in the outer region, you see there are 1, 2, 3, 4, 5. Next one, there are 5. And there's 1 in the middle. So 11. Again, V minus E plus F, number of match heads minus number of match sticks plus number of faces. Oh, somebody might be probably drawing on this. Yeah. Okay, again, so that becomes 20 minus 30 plus 11, which is equal to 1. So 31 minus 30, that's again equal to 1. Now we have drawn fairly regular figures for this. And I'm from Mumbai. So let's draw, we'll just try to see that this is a representation, this V minus E plus F, that happens very often. So you basically take any map of Mumbai is fairly easy. So what do? You take your map take any map, any political map from your atlas, and then you have these various regions that are there, and you put one blob for every region. Yeah, so north has, so this color coding that I have used here is just to make sure that there's some color contrast. So the yellow blob and red blob are not supposed to be different. They're just blobs. Yeah, so they're zero-dimensional, okay, vertices. And how do we draw edges? When two regions share a common boundary, not a point, but share a genuine common boundary, we introduce an edge between them. Yeah? So north has one vertex, east, west have vertices. So there are 1, 2, 3, 4, 5, 6, 7 vertices that we are introducing. And between north and this west, so between the green and this purple, there is a common boundary. So we draw an edge between them. Between north and east, between the green and the light purple, there is also a common boundary, this one. And so we draw another edge. So we draw this graph from any planar political map. And then we remove this graph, the same graph. Now we remove from the background from it. And we have this little graph on the right. How many vertices are there? 1, 2, 3, 4, 5, 6, 7 vertices. How many edges are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So number of edges is 9. How about number of regions? There's one upper triangle, then there is this quadrilateral. This is divided into two triangles. So that's another 3 faces. So there's 3 faces here. And again, you see that 7 minus 9 plus 3, again, it's equal to 1. Yeah. So V minus E plus F equal to 1 for any graph that can be drawn on the plane. So if two edges intersect, wherever they intersect, you introduce a vertex. Yeah? So that's called a planar graph. That means a graph that can be drawn on the plane. And this is really Euler's formula. This was the first discovery of a mathematical structure somewhere in the 1700s by Euler, where he proved basically that this is not something that's special to particular graphs, but any planar graph has this feature, V minus E plus F is equal to 1. And there's nothing special about Mumbai. You take any political map, exactly the same thing works. And it's not very hard to prove this basically by induction. Essentially, suppose this diagonal edge was not there. If you remove that edge, what will happen is that the number of edges decreases by 1. And two faces it was sharing, it was on the boundary of, those two become merged into 1. So number of edges decreases by 1, number of faces decreases by 1. And you have essentially reduced the complexity of the problem, and you can apply induction. So this is not very hard to prove either. So this was the first, what one can say, the first real theorem of one-dimensional geometry or one-dimensional topology. V minus E plus F is equal to 1 for any planar graph. And any map really works. So this graph is something that we call, as mathematicians, we say that this graph is dual to the map that we have drawn. So vertices correspond to regions, edges correspond to boundaries. Okay, so this is V minus E plus F equal to 1. Now so this is one-dimensional geometry. Now let's move on to two-dimensional Euclidean geometry, something that we study in school. And the first, one of these basic theorems that we learn when we are in school is that the sum of, you take any convex polygon you like, and you look at the sum of the exterior angles. What are exterior angles? You extend all the edges a little bit, and you look at the exterior angle there. Then you sum all these exterior angles, and you're going to get 360 degrees. So now let's again, okay, so we are going to we are just playing around with these basic figures, and there's this one basic feature that we use: sum of all exterior angles is 360 degrees for any polygon, for any convex polygon. So from this little simple observation, and how do we prove that it's 360 degrees? Basically, you look at the convex polygon and you move it parallel to itself till the 5 vertices become merged into one, and then the angles get distributed around it, and you basically see that it's really the angle around the circle, and that's 360 degrees. Okay, so let's start with that. Now ask ourselves, what are the internal angles? What are the internal angles of an equilateral triangle? Yeah. So internal angles of any regular polygon where all the sides and all the angles are equal. This is a simplifying assumption. It's not necessary, but it will make our life much easier. So first we want to look at all regular polygons. Yeah. Okay. So the sum of the exterior angles is 360 degrees. What is at any vertex, the sum of the exterior and interior angle is 180 degrees. So if you have an equilateral triangle, what do you have? The sum of the interior and exterior angle for 3 vertices is 3 into 180 degrees. And the exterior angle we have already observed is 2 into 180 degrees. So the sum of the interior angles is 1 into 180 degrees. This is just some slightly convoluted way of saying that the sum of the angles of a triangle, in this particular case an equilateral triangle, is 1 into 180 degrees. Fine. So what is each angle equal to? Just divide by 3, you get 60 degrees. Fine. Let's proceed with this next. Next is the square. So again, 4 vertices. Interior plus exterior at every vertex is 180. So total sum, interior plus exterior for 4 vertices is 4 into 180. The external angle sum is 2 into 180. That's the first statement here, always, for independent of the number of sides. So the internal angle is again 4 into 180 minus 2 into 180, which is this 2 into 180. So each interior angle is that divided by 4, which gives us 90 degrees. What about a pentagon? So again, let's do the same calculation. Again, it's 5 into 180 for interior plus exterior for all 5 vertices. External angle is 2 into 180. So the interior angle sum is 5 minus 2 into 180. So that's 3 into 180. So each angle is 3 into 180 divided by 5, which is 108. And so what happens is that in general, the interior angle sum is, if this number of sides is n, it's n minus 2 whole into 180. And so each angle is n minus 2 into 180 divided by n. So note that n minus 2 by n whole into 180 is going to converge to 180 as n tends to infinity, which means basically the sides are becoming more and more like a straight line. I mean, it's essentially going to converge to something like basically a circle. Okay, but this is all that we really need. And now we are going to use this to compute something that is 2-dimensional topology. Okay, let's move on to this next point. We take these polygons that are these polyhedra that are there. So these are what are called Platonic solids. Basically, it says that every face has the same number of sides. Every vertex has the same number of edges coming out of it. Okay. So now we ask ourselves the question. So you have these regular polyhedral shapes. You have these regular polyhedral shapes. Which one has a vertex which is sharper? And again, here the basic point is, how do we measure sharpness? So sharpness is essentially, imagine picking up any of these solids, poking yourself with it, and which causes more irritation, which causes more pain. And that's, if something causes more pain, we say that there is more sharp. All right, fine. So that's a qualitative way of measuring. But how do we give a number? How do we actually measure it? So here's the thing. For that, in order to measure sharpness, what we need to do is first fix a baseline, fix some baseline where we say that, okay, this is something that has no curvature at all. It is totally flat. Okay. So what is the sharpness concentrated at a point? So let's see. So if you had a plane that is flat, that means there is no curvature concentrated around any point there. So what is the total angle around a vertex in the plane, in the flat plane? So that is 360 degrees. So we take this naive measure, the angle defect, which means the difference between 360 degrees, which is the measure of, which is something that is going to give us something that's not curved at all, no sharpness at all, flat. And we look at the difference between 360 degrees and the sum of the angles at a vertex. So this angle defect is our naive measure of sharpness at a vertex. So we'll do again a few more experiments now with two-dimensional geometric figures. But the only thing I request you to bear in mind is that this sharpness at a point is measured by this angle defect, the difference between the sum of the angles and what would be the angle sum on a flat plane. This will be our measure of sharpness. Now we start measuring that. So let's start with a tetrahedron. What is happening here? So each face is an equilateral triangle. So we have already seen that each interior angle is 180 degrees divided by 3. So that is 60 degrees. But now you pick one of these corner vertices and you look at angle sum around that vertex. So how many faces are there? There are 3 faces. So the total angle is 60 plus 60 plus 60 around that vertex. And the total angle at a vertex is equal to 180 degrees, 60 plus 60 plus 60. So what is the angle defect? That is going to be, according to our formula, difference between 360 and the sum of the angles. So 360 minus 180. So there's 180 degrees worth of curvature concentrated at any vertex. This is going to change from polyhedron to polyhedron. And here is something that we want to, this is something that we just want to look at. What is the total sharpness? Which means now suppose you sum over all such vertices. We have the sharpness at a vertex 180 degrees, and the total sharpness is 180 plus 180 plus 180 plus 180, 4 vertices. So that's 4 into 180, that's 720 degrees. So the total curvature concentrated at these 4 vertices of the tetrahedron is 4 into 180, which is 720, which is essentially 4 times pi. Yeah, so pi is the 180 degrees in radians. So 4 times pi. So this is for a tetrahedron. Just as we did various experiments for different planar graphs, now we'll do a similar experiment for other polyhedra, other regular polyhedra. How about the cube? So each face is a square. Each interior angle, we have calculated that already, that's 90 degrees. How many faces are there at a vertex? There are 3 faces. There's this, in this vertex that you see staring out at you, there's a blue face, there's a yellow face, and there's a pink face. So total angle at the vertex is 90 plus 90 plus 90, which is 270 degrees. So what is our measure of sharpness? It's the angle defect, which is 360 minus 270 equal to 90. So measured this way, what was the angle defect at a vertex for a tetrahedron? It was 180 degrees. For a square, it's 90. So it has half the sharpness of a tetrahedron concentrated at a vertex. But what about total sharpness? How many vertices are there? There are 4 and 4, 8. So the total sharpness is 8 into 90, 720 degrees, 4 pi, which is the same as the one for the tetrahedron. Okay, so for cube, the sharpness at a vertex is 90, which is half the sharpness at any particular vertex for a tetrahedron. But the total sharpness, that means the sum of the sharpnesses over all vertices, remains the same, 8 into 90, which is 720 degrees. Let's do one more experiment for a slightly more sophisticated example, namely the dodecahedron. So what happens here? each face is a regular pentagon. We've already calculated the angle at that vertex, which is 108 degrees. Yeah, we've calculated this in the first slide of the second job of these two-dimensional geometries. How many faces are there at a vertex? There are 3 faces. So total angle at a vertex is 108 plus 108 plus 108, which is 324. So what about sharpness? The total sharpness is 360 minus 324. So that's the angle defect, which is 36. How many vertices are there? And this is a simple count. We've already done this count. There are 20 vertices, and each has an angle defect of 36 degrees. So total sharpness is 20 into 36, again 720 degrees. So we've done these 3 experiments for a tetrahedron, for a cube, for a dodecahedron, and we found that this total sharpness, which means the sharpness at vertices summed over all possible vertices, remains something unchanged. It is 720 degrees without, I mean, it's a uniform thing. It's a uniform number, independent of which regular polyhedron we've started off with. It's actually not a very hard exercise. And this is really, so we started off with Euler in 1 dimension, that was 1700s. Now we come to the 1800s, and this particular observation that we just now made for these 3 examples, this generalizes and it gives us what's called the Gauss-Bonnet theorem. This is probably, in some sense, the first really sophisticated theorem. This is the 19th century, 1800s. Gauss was around the middle of the 19th century. Bonnet was around a little after that. Basically says, take any convex polyhedron, any. So we've taken these 3 convex polyhedra, which are regular, but you look at any convex polyhedron, which means basically the sides are manufactured out of plain convex polygons, and you look at the sum of the sharpnesses over all vertices. The total curvature. Sharpness is measured by curvature. Sum over all vertices. It's always going to be equal to 4 into 180 degrees, which is 720 degrees. And this is not just for regular solids, which is where we have done these 3 experiments, but it is true for irregular solids as well, which means things where the number. So here in this figure, you have 1 hexagon, 1 triangle. The red is a hexagon, the yellow is a triangle, but still the sum of the sharpnesses can be measured and you still get a total sharpness 720 degrees. So this is a theorem of Gauss and Bonnet. Okay. So at this stage, we shall move up a couple of dimensions and ask essentially, okay, fine. So this was the 19th century. So what happens in higher dimensions, for example? So we are taking a short high dimensional excursion. So this number of vertices minus number of edges plus number of faces, this generalizes to what's called the Euler characteristic. What is it? It's basically this alternating sum, number of 0-dimensional objects minus number of 1-dimensional objects plus number of 2-dimensional objects minus number of 3-dimensional objects plus number of 4-dimensional objects, and so on. Yeah. So if you have a finite dimensional polyhedron of dimension n, so it's V0 minus V1 plus V2 minus V3, this alternating sum, that's called the Euler characteristic. So you have a combinatorial way of measuring some complexity. And this Gauss-Bonnet theorem in 2 dimensions. Yeah. So on the right side, you have these 3 pictures. On the left top corner, you have Gauss's picture. That's middle of the 19th century. On the right side, on the top right, you have Bonnet's picture, Pierre Bonnet. And these are the 2 people who proved the Gauss-Bonnet theorem from the previous slide, this theorem that I just talked about. And below that, you have churns. So this is a new person who comes in around the 1940s, and this is Shen Chern, who basically says that this Gauss, Bonnet, and Chern, the two of them together, the three of them together, proved a theorem which generalizes this statement that the sum of the curvature is invariant, and this theorem goes through for all even dimensions. It also goes through in odd dimensions, but then it's trivial. In all even dimensions, you have this Chern-Gauss-Bonnet theorem, which so in dimension 2, 4, 6, 8, etc., you have this kind of a statement which says that you sum the total analog of curvature in higher dimensions, and you do get something which is invariant, which depends only on what is called the topology, and that topology is given by this number called the Euler characteristic. So what have we done so far? We started with children's stick toys and sand drawings. We looked at mathematical graphs and networks. This is the one-dimensional exercise. Then we moved up one dimension and we looked at polyhedra and complex multidimensional shapes. And here we have that the basic lesson of geometry is that there is a unified picture that is given to all of this. All right. That's some kind of that's the point of studying geometry, where we look at all the visual information that we gather and then we collect it together in something unified. We find unifying principles behind all of it. Okay. Let's now revisit the Gauss-Bonnet formula, but now we shall not look at only convex objects. So recall, given any convex polyhedron, the sum of the sharpnesses that we had, this was the original Gauss formula, was 4 into 180, that was 720 degrees. Now the question is, what about other polyhedral surfaces? What about other polyhedra? Yeah, so which are not necessarily convex. Yeah, so here is on the right side you have a picture of something which is called a toral polygon. So it's basically like a seat, but it has a hole in the middle. So that's called a torus in mathematics. Okay, and here if you do this sum of you look at this v minus e plus f, what you're going to get is not plus 1, as in the planar polygons, but you're going to get 0. So what's happening is that if you take a sphere, which is basically the boundary, say some cells, so the boundary of a polyhedron is basically like a sphere, except that it has planar faces. If you blow it up, pump air into it, it's going to become nice and round and spherical. But otherwise, it's a polyhedron with some polyhedral surface on its boundary. But you can actually manufacture more complicated shapes, and these are these tori here. Yeah. So, for example, these are these tori. Yeah. And here, what has happened is that you've punched a hole inside a sphere, and it's basically like the surface of a donut or a surface of a bicycle cube, and but you've converted it into some kind of a polyhedral picture. And here, if you do your sum of angle defects, what you're going to get is for a total polygon, this is 0. Sum of the curvatures is 0. It's no longer 720 degrees. So this moves us towards finding a further generalization, and this is really the Gauss-Bonnet formula. So for that, we are really going to ask, what are all possible closed surfaces? Yeah. So we see the sphere, that's this globe that's there on the first picture. And then the one on the right of that is the torus. It's divided now into rectangles. And on the left bottom, you have essentially what mathematicians call a genus 2 surface. So you can think of it as two tori, and then you punch a hole in two of the tori and you tube them together. You get this genus 2 surface. And then on the right side, you have a sphere with 3 handles. And that's called a genus 3 surface. So the first I mean, this is again late 19th century. There was a classification of all closed orientable surfaces. So what are orientable surfaces? I'll come to that later. But there is a classification theorem. So any closed orientable surface is a sphere with G handles, which basically this round picture, that this green picture on at the bottom of the page, that's a sphere with 3 handles attached to it. So and the left top picture is a sphere with 0 handles. So a sphere with 0 handles is called a sphere. A sphere with 1 handle is called a torus. And then we just say sphere with 2 handles, the genus 2, sphere with 3 handles, genus 3, etc., etc. And so there's a classification theorem which basically says that this is all you can get. Any closed orientable surface is a sphere is homeomorphic to a sphere. I'll say what this homeomorphic means. Is homeomorphic to a sphere with G handles attached to it. All right. And then suppose you give each of these shapes a polyhedral structure, which means each it's converted into faces which are like polygons. Then what you get is that the Gauss-Bonnet theorem generalizes to all these surfaces and says that if you look at the sum of the curvatures, you get 2 pi, which is pi is the 180 degrees, so that's 360, into this multiplied by 2 minus twice the genus. So when genus is equal to 0, which is the sphere, you get 360 into 2, which is 720. When G equal to 1, which is the torus, you get 2 minus 2 in the inside, so that's just 0. And then after that, you get everything is negative. 2 minus 2 times G, that becomes negative. And so you get something negative for all the subsequent sums. So all of this has assumed this one word, homeomorphic to. So the way to think of homeomorphism is that two objects are homeomorphic if you can continuously deform without tearing one to the other. So here's the picture. So what is a homeomorphism? Essentially, so this is something I've already said. So for G equal to 0, 2 minus 2G is 2, which is greater than 0. For G equal to 1, it is equal to 0. And for G greater than 1, it is negative. So on the right side, you have this sequence of, well, it's dumbbells with 3 bells. So essentially, you start flowing, yeah. So there are these 2 thin necks. You start to flow. These thin necks are places where there's a lot of curvature concentrated, and the tips of the spheres are also have curvature concentrated, but they're curvatures of different signs. So you try to make things uniform, and you start flowing this dumbbell till it becomes something nice and uniform at the bottom of the page. Yeah. So you're flowing this dumbbell, and it becomes a nice round sphere at the bottom. On there's this other sequence where it's you basically take a very wrinkled up lemon and you start making it smoother and smoother till you come to a nice round lemon at the end. So all of these become nice round objects, yeah, and they are all uniform. So our hunt here is for, if you have any genus object, is there a way? See, what is the problem with these polyhedral objects is that there's curvature concentrated at finitely many vertices. So the calculation becomes very simple. You just look at the angle defect at each vertex, sum over all vertices, and you get a total curvature calculation. But what would be the best metric? So the best metric would be the most democratic metric. It does not value one vertex more than any other. Yeah. So all vertices are treated equally. So which means the curvature now has become smeared or homogenized over the whole space. So can we hunt for a best metric which values all points equally? So what do? We start with a polyhedral metric and think of that as these points as where curvature is concentrated. Think of that as like, say a heat source. But then you try to distribute the heat so that the temperature becomes equal all over the place. A slightly more sophisticated model of this is essentially the flow which allows, there is a flow, there is a differential equation which gives us a flow, which finally allows us to homogenize all this, this curvature. So we try to smear the metric till it becomes homogeneous. And in 2 dimensions, this kind of flow necessarily converges, and it's basically called Ricci flow. And it's a form of the RG flow in physics. And the culminating point of the Ricci flow are these constant curvature metrics in dimension 2. So there is this hunt for best metrics, and we can execute this in dimension 2 until we get constant curvature metrics in for surfaces. So essentially what we have is when genus is greater than 0, you have constant curvature +1. For genus equal to 0, you have constant curvature 0. For genus less than greater than 2, which means the Euler characteristic less than 0, you converge to a metric of constant curvature -1. So there are 2 problems here. The first one was topological classification or topological invariance. The second, now here what we are doing is hunting for a best geometric structure as opposed to purely topological, and we are hunting for the best metric, and then we do get in dimension 2 best possible metrics of either positive, constant 0, or constant negative curvature. So which means we are moving away from the polyhedral world into a smooth world where every point has the same kind of curvature. Okay. So this theorem is essentially the upshot of this Ricci flow. It's called the uniformization theorem in dimension 2. Every closed orientable 2 manifold, also known as a surface, it admits a metric of constant curvature. I haven't quite said what orientable is. Orientable basically means that there are well-defined sides. If you have a surface and there is an inside and an outside, you say that the surface is orientable. What is an example of something that is not orientable? Essentially a Mobius strip. If an ant starts crawling on a Mobius strip and then makes one round around the Mobius strip, it's going to come back to the same point, but it's going to face the other way, face the opposite direction. So that's something that's non-orientable. But if that's not the case, if there is a well-defined inside and a well-defined outside, which means normals pointing in correct directions, we say that the surface is orientable. So this uniformization theorem gives +1 constant curvature, +1 for the sphere, 0 for the torus, -1 for genus greater than 1. So we have now 2 theorems. One is a classification theorem for closed orientable 2 manifolds. Every closed orientable 2 manifold is a sphere with G handles. G could be 0, 1, 2, 3, 4, etc., which means we have now defined dockets. And if you give me any closed orientable surface, there is one and only one docket, which is given by a number, the number of handles, into which I can put. So this is a topological classification. The geometry is essentially saying that, well, you start with any of these. Is there a best possible metric which is homogeneous? And the answer is yes. Okay. So now having learned this, so this uniformization theorem is called the Poincaré-Quebec-Klein uniformization theorem in dimension 2. Again, it's very late 19th century when this was proven. This was at the end of the 19th century. And the problem which was posed by Poincaré, essentially a problem which we'll come back to a little later, called the Poincaré conjecture, essentially is the simplest test case for classifying manifolds in higher dimension, in dimension 3, 4, etc. This is the point of our, in the title, we have done 1 and 2. Now we are going to 3, 4, etc., etc. So there are 2 problems. One is the problem of topology, classify manifolds in dimensions 3, 4, etc. And there's a problem of geometry, which is basically finding the best possible metrics. So these are the 2 main problems which determined the Essentially, understand the topology of high dimensional manifolds, understand the geometry of high dimensional manifolds. That's what these two problems, problem 1 and 2, are supposed to be. And this took, and the final solution really happened in the 21st century, so more than 100 years. Yeah? So we'll get to that right away. Yeah. But let us before getting to dimension 3, let me say why this particular problem, the classification problem, is not solvable in a formal sense in dimension greater than 3. And here's the point. You take any finitely, so this is now we are going to move it towards some group theory. So take any finitely presented group, which means you look at words in some finitely many symbols, in n symbols, G1 through Gn, and you're allowed inverses. And you declare that if you have a subword which is again chosen from some finite set, R1 through Rs, those words are declared to be the identity. So for example, if you have the group Z plus Z, then you have two generators, G1 and G2, or A and B. And there's one relation, AB, A inverse, B inverse, which means basically AB is equal to BA. You're declaring AB, A inverse, B inverse equal to 1, which is the same thing as saying that AB is equal to BA, where your generators are A and B. Okay. So for that, what you do get a two-dimensional surface, namely the torus. And so here's the basic point. This is again proved. Now this is 20th century, 1940s thereabouts. Any finitely presented group, it can be realized as the fundamental group of a two-dimensional complex. Yeah. So basically, there is a two-dimensional complex, which means you have some collection of loops, all based at a point, and you take your two-dimensional cells corresponding to these R1 through Rs, polygonal cells, and their boundaries are glued to these generators. So if your R1 is A1, it is G1, G2, G3, and there are three generators, so you take one two-dimensional cell, and you break the boundary into three arcs, and then each of these arcs are now glued along G1, G2, and G3 in that order, and you've glued in a two-dimensional cell. So this is not quite a, I mean, it's called a two complex because you start with some one-dimensional cells and you glue in two-dimensional cells. And here's the next thing is that you look at this, you start with this two-dimensional complex. It's an abstract complex. It's not necessarily embeddable. I mean, if you try to force this thing to be embedded in 3 dimensions, you might have self-intersections. And here's the theorem, which basically says that it can be embedded in Rn, so in higher dimensional space, for all n greater than or equal to 5. And this crucial number is very important. This is called the Whitney embedding theorem, essentially. It says that in order to embed a two-dimensional or some k-dimensional complex, you need at least 2k plus 1 dimensions. Yeah. So essentially, I mean, intersections are, you want the intersections, self-intersections to be empty. So now, once you have embedded this, then what you can do is thicken this two-dimensional complex, take a little neighborhood of that, and then what do you get? You get an n-dimensional object, but it has boundary. And so the boundary of this thickening, that gives you an oriented manifold of 1 dimension less than Rn. So if you take your two-dimensional complex, embedded it in 5 dimensions, take a little thickening, take the boundary of the resulting 5-dimensional manifold you've constructed, you get a 4-dimensional manifold whose fundamental group is the same as the finitely presented group G that you started off with. Okay? So why am I getting into this detour into fundamental groups? And the point is that if you had a classification of manifolds, then just going to this fundamental group, yeah, of the manifold is losing a lot of information. But even after that loss of information, theorem basically says that you cannot classify these groups. So if you take any two finitely presented groups, which means you have two such presentations, G1 through Gn, R1 through Rs, and then H1 through Hm, L1 through Lk, two different groups, there is no algorithm that you can come up with which will tell you whether these two groups are isomorphic or not, which means as abstract groups, whether they represent the same object or not. So if you had a classification possible, which means in particular that you're given two presentations, you have an algorithm which in finite amount of time tells you these guys are isomorphic, yes, which means the same as groups, or they are different, no, they are not isomorphic as groups. Such an algorithm does not exist. There's a formal theorem, precise theorem, because if you could solve this, then you would solve what is called the Turing machine halting problem. So this is some paradigm of computer science. So in dimensions strictly greater than 3, no classification result is possible. This is a theorem. This is not just that it's very hard or very difficult. It's nobody, given our present paradigms of computation, of classifiability, this classification problem in the sense of classification as we know it is not possible in dimension 3, dimension greater than 3. Fine. So as far as those two problems that we had posed in the previous slide, classical manifolds in dimension 3, 4, etc., etc., there's already a theorem which says that this problem does not have a solution. Theorem it does not have it says that it does not have a solution in dimension 4 or more. And therefore, the geometric problem, which is more sophisticated, find the best possible matrix, is also not solvable. So we are left with the final frontier, which is dimension 3. Beyond dimension 3, it is not possible. That's what this theorem says here. There is no classification possible in dimension greater than 3. So what about 3 manifolds? So in dimension 2, we had this nice thing. The genus was equal to 0, 1, 2, 3, 4. There was this nice list indexed by 0 and the natural numbers. And every 3 manifold was fit into one of these schemes. Every 2 manifold fit into one of these schemes. But the classification of 3 manifolds, and the good part, I mean, the happy part of the story is that really it can be done. It has been done in principle. Really, it becomes a completely crazy world. It is possible to classify, but it is actually, I mean, even the classification of the animal kingdom is a much simpler process. I mean, and this is really what it looks like. It looks totally crazy, where, I mean, I don't know whether people know this or not, but apparently the whale and the pygmy hippopotamus are supposed to be very closely related in terms of evolution. Anyway, so I've drawn some pictures here. I mean, we collected some pictures from the internet here. Essentially, this is just to give you the impression that the animal kingdom classification is a pretty complicated process. Yeah, it does not have this nice, neat description that you have for 2 manifolds, genus equal to 0, 1, 2, 3, 4, etc., etc. If you try to classify those 3 manifolds, well, it can be done due to the work of many very strong, very top-level mathematicians. But the classification output is a difficult classification output. Yeah? So it can be done. It is in principle possible, but it's not easy. Okay. And these are the people who are at the forefront, or who have contributed the most towards this classification. And why did I bring out this problem of what is the best geometry? It turns out that the classification of this easier topological problem really proceeds by solving this harder problem of finding the best metric. So the first question that was asked was essentially by Poincaré. This is the person on the left. Yeah. He posed this question in 1905, and that question is called the Poincare conjecture, where he asks if the fundamental group of a closed three manifold is trivial, yeah, simplest possible situation, the group theoretic information is trivial information. There is no fundamental group. And one object, one closed three manifold which does have that fundamental group is the three-dimensional sphere, x square plus y square plus z square plus w square equal to 1. And so Poincare asks if any three manifold whose fundamental group is trivial is homeomorphic to the three sphere or not. This was the Poincare conjecture. He first asked an easier question, but that had counterexamples. He himself found the counterexamples, and then asked this harder question, the Poincare conjecture in dimension 3. And that got solved around 2004. And the person at the top right, that's William Thurston, he took the Poincare conjecture and generalized it considerably to apply to all three-dimensional manifolds, and conjectured that any three-dimensional manifold can be decomposed in a canonical way into pieces which have best possible metrics. What this conjecture means and what are the best possible metrics is going to be the subject of the talk after we take a break. But right now, I'm just telling you the history of this problem. So the classification result, Thurston conjectured, topological classification result, Thurston conjectured, should go through this understanding of best possible geometric structures. And he conjectured this in 1982. Far-reaching generalization of the Poincare conjecture. And the problem was solved in 2004 using three-dimensional version of this flow of metric of RG flow or Ricci flow. And the gentleman who did it is this person at the bottom, Grisha Perelman, person with the beard at the bottom in the colored photo. And he proved this, and in particular, he proved that the Poincare conjecture is true. So there are 7 problems that were designated at the turn of this century as millennium problems. And each problem, basically 7 problems which are supposed to, signify the most fundamental open problems in mathematics. And the only one that has been solved so far is the Poincare conjecture as solved by Perelman. Okay, good. So after this, once that Poincare conjecture is solved, and this stronger conjecture of Thurston, also called the geometrization conjecture, which means topology determines geometry, determines best possible metrics, also solved by Perelman. Once these are solved, the classification does go through. How it goes through and what are the details, what are the mathematical details, is something I will come to in the next talk after this. But here, we can say that both these results, both these problems that I had posed in the two-dimensional world, classify manifolds in dimension 3, find best metrics. 4 and above, we've already seen cannot be done. So the only problem that remained was classify manifolds in dimension 3 and find best metrics in dimension 3. And both these problems do get solved after Perelman's resolution of the geometrization conjecture. And so essentially this last frontier has been crossed. Three-dimensional manifolds are now essentially understood as far as the topology and the geometry are concerned. But once you have that, then you have further problems. Essentially, how do you connect it up with other kinds of geometries? Here we are looking at the best possible metrics, but then there are other possible geometries. And so once you have the background ready, the frontier is pushed back. And now we ask questions about, are there more sophisticated structures which these geometries understand? Okay. So thank you for the time for now, and we'll resume with three manifolds after a short break of 5 minutes. Okay, so now let's start. So we finished the previous hour by saying that this classification of problem for three manifolds is possible, and it has probably been the most fundamental advance in geometry and topology over the last 100 years or so. And so we'll now try to say something. It's not possible to summarize 100 years of work in 1 hour, but I'll try to give you the salient features of what are the steps that are necessary in solving this classification problem of three manifolds. And as I said, the solution really goes through trying to find best possible geometries. So now on to three manifolds. So the study of three manifolds, it turns out that this is intimately, essentially a huge amount of the information of the study of three manifolds is really contained in the fundamental group. So this soft topological invariant, the fundamental group of the manifold, turns out that it contains almost all the information that is required, that you require. You don't require more. And that's the upshot of this geometrization. So here's how we'll denote. So M will be denote three manifold for this particular 1 hour, and pi 1 of M will denote its fundamental group. Okay. So the story starts somewhere, again, 40s or so, and this is a theorem by somebody called Papakyriakopoulos. What he did was the following. There are groups which record higher dimensional spheres. So essentially you look at, so there's these second homotopy groups which are called pi 2, and the base one, which is pi 1, is called the fundamental group. So pi 2 basically records, suppose you just look at maps of a two-dimensional sphere into a three manifold, and which try to classify such maps which are not contractible, which means that you map your, if you just take an S2 inside three-dimensional R3 and you map it whichever way you like, you will be able to contract it down to a point. But suppose that there are examples of such spheres which can just be mapped in but cannot be contracted to a point, then we say that the second homotopy group, pi 2 of M, is non-trivial. What this theorem says is that if pi 2 of M is non-trivial, then something very restrictive has to happen. What it says is that it contains a two-dimensional embedded sphere, or a projective plane, which we don't need to bother about for this talk, an embedded sphere. So you're just looking at, the hypothesis says that you take just any continuous map of a sphere which can intersect itself. The output of the theorem says you can convert that map into an embedding, so which means that it does not have self-intersections, and the output says that this particular sphere is also, it cannot be collapsed to a point. So if you have just a continuous map, the sphere theorem says you have a continuous embedded map. You have a continuous embedding. What's the use of this? It's a two-dimensional sphere embedded in some three-dimensional manifold. It allows us to cut the manifold along the embedding. You can't cut a manifold along something that self-intersects. But if it's embedded, you can cut your manifold along it. Yeah? So here's the thing. So for now, this is something I've already said. We shall not regard these. They add a little bit of a wrinkle, but it's not very important. So we'll always think of closed orientable three manifolds, and we'll ignore projective planes. Yeah. So then what you can do is you can cut your manifold M. So you have some sphere, two-dimensional sphere. That means it has two sides. You cut your three manifold along that, and then what results is now you have a manifold with boundary, with two boundary components, one for the plus side of the sphere, one for the minus side of the sphere. So you now, after cutting along the sphere, as you cut along sigma, you get M minus sigma. Now this has M minus sigma has two boundary components, M minus, so sigma plus and sigma minus. And those are two-dimensional spheres. There is a natural way to fill in a two-dimensional sphere. You by hand, you glue in three-dimensional balls to these boundary spheres. So you fill in these balls and you get simpler manifolds. Suppose sigma is separating. If that means that M minus sigma has two pieces and they are not connected. Yeah. So basically you cut open along a sigma and you've really separated your manifold into two different pieces, two disjoint pieces. And then it turns out that the original manifold can be obtained from these simpler manifolds M1 and M2 by a process called the connect sum operation. That is this hash here. So simpler manifolds can be used to build up a larger manifold M. So M1 and M2 are simpler manifolds, less S2s as quantified by the sphere theorem. And the other possibility, which is a very restrictive possibility, is that sigma is non-separating, which means you cut along sigma, you still get one connected object. This essentially says that, well, your original manifold had contained a product S2 cross S1. Yeah, so that M is a connect sum of this S2 cross S1 with some other manifold. So what is this mysterious connect sum operation? It's nothing mysterious, it's something very simple. What this allows us is you can take three manifolds and you can decompose them into simpler pieces. So what do? Suppose this cutting was taking something complicated and getting it into simple objects. So what is the reverse operation? Suppose you start with simple objects, start with connected oriented three manifolds. Then the oriented connect sum of M1 and M2 is obtained. How do you do this? You take these two three-dimensional manifolds, take points in the two different manifolds, and you carve out a little open ball around one. You carve out a little open ball around the other. Then you have two three-dimensional manifolds whose boundaries are spheres. Glue those spheres together. So remove a small open ball from both and glue the resulting boundary. This is not very important, by an orientation reversing homeomorphism, just to retain orientability. Yeah. So this process is called connect sum operation. So what the previous thing was saying is that once you have an embedded essential sphere, which means that the sphere cannot be contracted, you can decompose your manifold into this kind of connect sum, into a connect sum of simpler objects. This allows us to ask, what is the simplest class of three manifolds that you get, which means manifolds which cannot be non-trivially decomposed into connect sums. So if for any connect sum decomposition, M is connect sum of two simpler objects, M1 and M2, one of them is necessarily the three-dimensional sphere, the simplest manifold. So if you remove a small ball from the three-dimensional sphere, what you have left is another three-dimensional ball. See, if you take two disks and glue them along their boundary, what do you get? You get a two-dimensional sphere. Similarly, if you take two three-dimensional balls and glue them along their boundary sphere, you get a three-dimensional sphere, S3. Yeah. So connect sum with S3 is a trivial operation. You get your original manifold back. It's basically something like 1 multiplied by any number is the number itself. Yeah. So, but if you cannot do this decomposition, so if the only possible connect sum decomposition is the simplest one, namely with S3, then you say that the manifold M is prime, which means that you cannot decompose it into simpler pieces. Yeah. So these are the building blocks under this connect sum operation. Manifolds which cannot be decomposed, cannot be prime decomposed further, are called prime three manifolds in analogy with prime numbers. So, well, fine, that's fine. This is an operation. You can keep on decomposing. But what tells you that such a decomposition is at all possible? Well, we've given some definitions, so we need to prove something. And so here is the prime decomposition theorem. This is not hard, but when people came up with it, it's a sophisticated idea. So M is a compact three manifold. First, this is by Kneser, theorem by Kneser, proved that a prime decomposition exists. Yeah. So, which means basically you take any three manifold you like, it can be decomposed as a connect sum M1 to Mk, where each manifold Mi is prime. This is a theorem that was proven by Kneser. Fine, that's helpful. But then we get a little greedy and ask, well, is the prime decomposition unique? Yeah, just as multiplication. I mean, if you take any integer, you have a prime factorization. That prime factorization is unique up to just rearrangements of the prime factors. Is the same true for manifold, for three manifolds? And the answer indeed is yes. Further, such a decomposition is unique. This was proved by no less a person than Milner. Yeah, so Milner proved that this prime decomposition, Kneser proved it exists. Milner proved that it is unique. Okay, so that makes our life fairly easy, which means now we no longer need to look at all possible three manifolds, all possible closed three manifolds, but we can devote our analysis only to prime closed three manifolds. So this previous theorem, the sphere theorem, basically now says that either there are no two-dimensional spheres which cannot be contracted, which means pi2 of m is 0, or it is just this simple object, this product of a sphere with a circle. Yeah? So essentially, if you exclude the sphere across S1, what has happened is that you've reduced the understanding. I mean, this really basically says that pi1m, this fundamental group, is the last real algebraic storehouse of information about the manifold. Okay, so that's what prime decomposition tells you to do. And now, what about higher things? I've said 1 and 2, but then there is some problem. What about 3? And this really was captured by Poincaré when he talked about his Poincaré conjecture. So what is the Poincaré conjecture? Now let's formally state it. It asks, suppose you have a closed, simply connected three-manifold, which means no fundamental. And Poincaré conjectured that it is homeomorphic to the three-dimensional sphere. This was solved by Perelman. Okay, in 2004. So assume that assume therefore that our manifold M, three manifold, is prime. It cannot be decomposed along by this connect sum operation. And you assume that it is basically not the sphere across S1. I've not written covered by. This is to exclude this projective planes, but essentially you will be fine if you just think that it is not the sphere across the circle. Then the theorem basically says, once the Poincaré conjecture is solved, it basically says the following. So there are two possibilities. The fundamental group is either finite or infinite. If it is finite, then the universal cover, yes, so this is a manifold, this is the topological space, so you can pass to the universal cover, which means the smallest simply connected object which admits the projection down to the manifold, and it's by covering transformations. Then the universal cover necessarily has to be the three sphere. Why? Because because it's finite and M is compact, the universal cover is also compact, but it's simply connected. Therefore, by the Poincaré conjecture, it is the three sphere. The other possibility is that the fundamental group is infinite. And in this case, it turns out that the universal cover is homeomorphic to our standard Euclidean three space, but without any metric. Yeah? Topologically, it's just the standard three-dimensional space. The second statement is not a trivial statement. I mean, just the statement that it is covered by something that is topologically the three-dimensional space that we live in. This is a consequence of Thurston's geometrization conjecture proved by Perelman. So this geometrization conjecture, it turns out, is a much harder question than the Poincaré conjecture. And it's also solved by Perelman. Okay. Without geometrization, so prior to the solution of geometrization, all that we could conclude is that the universal cover is contractible. So if you have a contractible three-dimensional manifold, it is not clear at all that it is. In fact, there are examples due to Whitehead there are contractible three manifolds which are not homeomorphic to our standard Euclidean three space. It was not known whether such manifolds cover compact manifolds, and what the geometrization conjecture resolution proves is that no, none of these exotic examples that Whitehead and company discovered, none of them have groups acting on them co-compactly. Okay. But after geometrization, the situation is a happy situation. They are all covered by Euclidean 3 space. So really now what we are now, so this is after the resolution of the conjecture, but what was the kind of structures that went into the resolution of this conjecture? So let's get back to prime free manifolds. We have decomposed M along, so I mean, this previous slide is basically just to tell you where we are headed, yeah? So I'm just I'm restating the Poincare conjecture and the geometrization conjecture and what goes into it. I mean, what is the content of the statement? Now let's get into some ideas, some basic ideas of the proof. So we have decomposed M along these essential two-dimensional spheres to get prime pieces. Can we do some further decomposition? And for that, so here's the point. What are we going to decompose along? A two-dimensional sphere is a two-dimensional object sitting inside a three-dimensional manifold. That's how we could decompose our three manifolds. What if other two-dimensional objects sat inside the three manifold? This is the question that we will be looking at. See, in the previous first hour, we discussed this classification of two manifolds. Any closed orientable surface is a sphere with G handles. G could be 0, 1, 2, 3, 4, etc., etc. G equal to 0 is the existence of an essential sphere, and this prime decomposition allows us to handle such objects. It allows us to cut this manifold along these spheres and get simpler pieces. But what if there are higher genus surfaces embedded inside a three manifold? Well, as we said, the entire information is contained in the fundamental group as far as the soft topology is concerned. So we want some information at the fundamental group level also. So a compact orientable irreducible three manifold is Harkin. This is the name of a person, the same person who solved the four color conjecture. Every map and every planar map can be colored by four colors. He and Apple solved that. So a compact orientable irreducible three manifold is Harkin if it contains a properly embedded two-sided essential surface sigma. Yeah. So if you replace S2 by some sigma, some genus G sigma, then you have this embedded surface, and you require that. Yes, David, go ahead.
Yeah, I have a question. It was not clear for me why before we assume the space M cannot be covered by the Hopf vibration.
The Hopf vibration is a Hopf vibration of S3, right?
Yes, yes. You assume that it shouldn't be S2 cross S1, but why we assume that?
So if you what's the other the Hopf vibration? Okay, so this is the one case. So if you look at the Hopf vibration, then what is the universal cover of that? The universal Hopf vibration is the projective plane. It has fundamental group Z mod 2Z. If you look at the Hopf fiber is actually covered by S3. So if you look at a two-dimensional, twofold cover of that, you get S3 back. So there, my statement was essentially the tilde. I did not quite define it. I said it quickly. M tilde denotes the universal cover, which means the smallest simply connected object covering our manifold. The Hopf vibration is not simply connected. It has fundamental group Z mod 2Z. So if you look at its universal cover, you get back S3.
Okay. Thanks.
Okay. So that's the second statement here. I mean, so either prime and it's not covered by S2 cross S1, this is still infinite fundamental group. Or two cases remain. See, the Hopf vibration does not have pi2. This was the case. This S2 cross S1 is the case where the second group, this basically you have a two-dimensional sphere which cannot be contracted. The Hopf vibration, if you map a two-dimensional sphere in there, you can contract it down to a point. So really what is left is things with finite fundamental group, which means the Hopf vibration has fundamental group Z mod 2Z, it is covered by S3. So this first statement, pi1m is infinite, then the universal cover is S3, that excludes that case. Is that okay?
Yes, yes.
Okay. So now we have decomposed M along two-dimensional spheres. Yeah, I am not being able to see the chats unless you raise your, so yeah, I saw that you had raised your hand, so I can address that. But since I'm on full screen mode, I'm not getting the chat. So in case there is any question, please interrupt. Yeah. Okay. So now we look at three-dimensional manifolds where not just S2s, but there are higher genus surfaces also embedded, such that the fundamental group is respected. So which means that the fundamental group of the surface injects into the fundamental group of the manifold. So these are called Haken manifolds. And really these were the principal tool that Thurston used to construct geometric structures on a large class of three manifolds. And then he constructed it on a large class and then conjectured it can be done for everything. And that can be done for everything was solved by Perelman using very different methods. Okay. So this is our Haken manifolds. And so we are really asking, well, take any closed orientable surface, sphere with G handles, and suppose that sits inside your three manifold, respecting the fundamental group. So for G equal to 0, we have the sphere decomposition. Now there is this one strange case which is intermediate, namely the G equal to 1 case. Yeah, so tori. So the point here is that we had mentioned that somehow genus equal to 0 is special, that has positive curvature plus 1. Genus equal to 1 is also special, it has 0 curvature. But everything else falls into one basket. Everything else admits a constant negative curvature. So somehow there's a natural classification of two-dimensional manifolds, which is even simpler than this genus classification, which is plus, 0, and minus, where only sphere fits into 0, only torus fits into, only spheres fits into plus 1, only torus fits into 0, and everything else is negative curvature. So we've done this sphere decomposition. What about decomposition along the next simplest object? What about tori? So can we do a decomposition of three manifolds along tori? So now we decomposed manifolds into prime manifolds. Now we want to decompose along tori. So we'll do a further decomposition. And so essentially, if you have a torus, which means, again, and go back to this definition of Haken, suppose you had a torus which did sit inside, and then what is the fundamental group of a torus? It's a simple object, Z plus Z. And suppose that this torus, there's a map from the torus into the three manifold, which is injective at the level of fundamental group, which just means that the fundamental group of M contains Z plus Z. Okay, so how about tori? Suppose you have just this Z plus Z sitting inside your three manifold fundamental group. Does it give you restrictions? Does it give you global topological restrictions? So that's the question that we are asking. And the answer turns out that yes, actually, there are very non-trivial restrictions that you can get just out of this simple restriction, that simple algebraic condition that the fundamental group contains a Z plus Z. So here is the torus theorem. So this is now already in the 70s. This is 1970s. It's basically proved by Jaco, Shalen, and Johansson. Suppose M is a closed prime three-manifold. Irreducible basically means it's prime and not S2 cross S1. Yeah, that's the basic thing. Suppose M is a closed irreducible, so it's just a word to put those two things together. Suppose M is a closed irreducible three-manifold. Then what happens? Just this fundamental group information. Yeah. So we assume, yeah, okay. I haven't put the hypothesis. The hypothesis is there in the question above. Suppose Z plus Z is contained in the three-manifold. Yeah. So that's the hypothesis. The question, sorry, I should have put this here. Suppose Z plus Z also is contained in the three-manifold. Then two possibilities happen. Either just Z plus Z again, it's something like it's the analogous situation to this sphere theorem. Just existence of Z plus Z means that there is a map from the two-dimensional torus into the manifold, which can intersect itself, but at the level of fundamental group, it injects. What the torus theorem says is that, well, you can actually convert it into an embedded object. So either M contains, see, embedded objects are very nice. As soon as you have embedded incompressible objects, which means that the fundamental group injects, you can cut along such surfaces. You get simpler pieces. That's what we did in the torus theorem. So suppose you have M closed irreducible three-manifold and the fundamental group Z contains Z plus Z, then either you can find an embedded torus which has Z plus Z in it, and so it's an embedded incompressible torus, or this other option which does occur is also quite simple. It has the fundamental group has a normal subgroup. It has a normal subgroup which is infinite cyclic. See, if you have a normal subgroup, then basically you take any other element, then it has to normalize. So if you have Z normalized by something else, essentially you have to have Z plus Z in it. Yeah, it's up to some finite index. That's always the case. Yeah? And so the torus theorem says that these two are the only possibilities. Either the whole three-manifold has a normal infinite cyclic subgroup, or it contains an embedded incompressible torus. These infinite cyclic normal subgroups, they come up in a fairly standard way. So essentially, if you have a bundle over a surface, yeah, say a circle bundle, say take the two-dimensional surface of genus something, 2, 3, whatever. And then you look at the unit tangent bundle to that. So that's a circle bundle over a surface. And that circle fiber, that necessarily contains a normal subgroup, which is infinite cyclic. So essentially what this torus theorem is saying, that either you have an embedded torus, or as far as fundamental group is concerned, it looks like a bundle. So the group theoretic version of a bundle is essentially this infinite cyclic normal subgroup, a circle bundle. But then what you want to do is you want to resolve this case 2 further. You want to understand, this seems to be a somewhat simple, but it's an exceptional thing. In the first case, either M contains an embedded incompressible torus, you would just like to cut along that torus. But what are you going to do with the second case? So that brings us to this next definition, which has found a lot of use in the physics literature relatively recently. So a compact closed three-manifold is called Seifert-fibered, yeah, if it is foliated by circles, which means you can decompose the space continuously as a union of circles. Yeah? Such spaces are called Seifert-fibered. And Epstein basically described the structure of such Seifert surfaces. What Epstein proved is that if you have a foliation by circles, it's really a circle bundle, which is a stronger statement. What he proved is that you take any circle leaf of that foliation, then he proved that it has a neighborhood that looks like a solid torus, and the solid torus is constructed in a very specific way. You take just the disk cross I, yeah, just to take the round disk cross I, and you glue the top to the bottom, where you twist around by a rational angle, 2 pi, rational multiple of 2 pi, 2 pi times p by q. What happens is that there is a special fiber here. The core circle, 0 cross 1, becomes a core circle, and the nearby circles are now union of p copies of this vertical interval, or q copies of that vertical interval. Yeah? So essentially, what happens is that you the look at the torus, the usual torus, and you look at the p by q slope line. Yeah, and those p by q slope lines, those will close up to circles, and those are called torus knots. So each nearby circle winds q times around c and sits on the boundary of the neighborhood like a PQ torus knot. So it's basically like just this P by Q slope line on the torus. But the core, so in the core circle, it just goes straight up from the origin of the disk to the top of the disk, and the nearby every other fiber, it rotates around it. So Daniel, you were talking about the hop vibration. There, what you have is essentially the 1-1 slope. Yeah, so you have a solid torus in the middle. There's a core curve, and the boundary curves are all this 1 by 1. So P and Q are both 1, relatively prime. Yeah, so that's a special example. Okay. So just from a decomposition of the space into circles, you have this further structure. Each nearby circle, it has a bundle structure, so it fibers. Yeah? So it is like a circle bundle over a space. What is that space? That space is not quite a surface, but it's very close. So if the Q is large, greater than 1, these are called singular fibers, and it's relatively easy to show that there are only finitely many such singular fibers. All the other fibers are called ordinary fibers. And if you collapse all these circle fibers to points, what you get is not a two-dimensional surface, but what you get is something called a two-dimensional orbifold, which means these singular fibers, there are finitely many of them. You have a two-dimensional surface, but then you have these finitely many points on them, which correspond to singular fibers. And there's a kind of a rotation about them, which is recorded upstairs. So this basically, it's like taking a two-dimensional disk. You fix the center, and you look at the Q-fold rotation. Yeah? So you're going to get a little cone. Yeah? Topologically, it's just a two-dimensional surface, but geometrically, there's a cone structure. So these objects are called two-dimensional orbifolds. So really, all Seifert fiber spaces are circle bundles over orbifolds. Yeah? So what did we do here? We started with this compact free manifold, which is foliated by circles, and we proved that such an object has a restricted topological structure, namely it is a circle bundle over a two-dimensional orbifold. Why am I talking about Seifert fiber spaces? Yeah, okay, so this is just saying that the singular fibers become the orbifold points, and it gives, a PQ singular fiber gives you an orbifold point of order Q. But why am I talking about Seifert fiber spaces? And this was because of this case that we had in the torus theorem. Let me state the structure. This is simply fundamental group giving you a lot of information. The Seifert fiber space theorem says, suppose M is irreducible, and suppose pi1 M contains an infinite cyclic normal subgroup. This is soft topological information. This is again a result of many people's work. Then M is Seifert fiber. So just given this information of an infinite cyclic normal subgroup, what you conclude is that the manifold has to be very controlled. It is a circle bundle over an orbifold. If you are not very familiar with orbifolds, just think, this is an equivalent definition. Just think of a finite group acting on a genus G surface for some G, and you look at the quotient. Yeah, that's the Seifert, that's an orbifold, and then you have a circle bundle over that. So basically, that's so essentially the Seifert fiber spaces are those that are covered, finitely covered by circle bundles, genuine circle bundles over genus G surfaces. So these are all Seifert-Fibon spaces. They are very controlled objects. And this theorem was proven by Jeff Mess, Tukia. Oh, I've written Tukai. It should be Tukia. Tukia, Gabay, and Casanung-Rice. Okay. Let me just go back to where we had brought in this object and go back to the torus theorem for a moment, and then we'll go. Yeah. So what did the torus theorem say? Suppose your fundamental group contains a Z plus Z. Then either you have an embedded incompressible torus, or the fundamental group has an infinite cyclic normal subgroup. The Seifert-Fibon space theorem basically says that the second option gives you that the manifold M has a very controlled topology, namely it is a Seifert-Fibon space, which means it is foliated by circles, which means it's a circle bundle over a two-dimensional manifold. So basically, the geometry is very simple. It almost splits. There's a two-dimensional base, there's a one-dimensional fiber, and the combination of these two things give you your whole three-dimensional geometry. Yeah. So it's, in some sense, you can decompose the three dimensions into a two-dimensional base and a one-dimensional fiber. So it's still quite simple. Still quite simple. The other case that is there is when you can cut along an embedded incompressible torus, and it turns out that this really is the most sophisticated geometry that you can expect. I mean, see, here's the, yeah, so now let's proceed with that. So let's get back to this Seifert-Fibon space theorem, which allows us to reduce the study of the torus decomposition to embedded tori. So you start with prime M. If you have an infinite cyclic normal subgroup, you're happy. If not, and you have a Z plus Z, then you can decompose M maximally along embedded incompressible tori, which means you can cut along these objects. There's no canonical way to fill solid tori in, so you leave those boundary components hanging. Yeah. So what happens after you have done this decomposition? After this decomposition, what remains? So this just one thing that you should note is that in order to cut along such tori, you need a Z plus Z in the fundamental. It's not necessary that Z plus Z is contained in the fundamental. So which means that the number collection of tori might be completely null. There might be just no tori. So what are the geometric pieces that you get after cutting along such thing? One, you get Seifert-Fibon spaces, pieces. Or, so this is a theorem, this is really the geometrization. Or you get hyperbolic pieces, or you just get a product. So just take a torus and take a product with a circle. That is a circle cross circle cross circle. That still has a torus cross a point sitting inside it. It's a torus embedded. It's fundamental group inject, so you can cut along. So the torus decomposition gives you either torus plus 0,1 or Seifert-Fibon pieces or hyperbolic pieces. This really, it's a paraphrasing of the geometrization conjecture, and this is what was proven by Perelman. So this really was conjectured by Thurston and proved by Perelman. So then what happens? What are hyperbolic pieces? What are hyperbolic objects? Hyperbolic objects basically means that the universal cover of the manifold, so the manifold admits, okay, so I think the simplest way to say it is that the manifold admits a complete metric whose curvature is, the sectional curvature at every point is -1, constant. Recall that in 2 dimensions, we had these genus greater than equal to 2 surfaces. And what we proved was, I mean, what the uniformization theorem proved was essentially that all of these admit constant -1 curvature metrics. And in 3 dimensions, a similar thing could happen, which means a manifold, a 3-dimensional manifold is hyperbolic if you take any point and you take any plane in the tangent space, the curvature on that plane is constant -1. So for any choice of a point, any choice of a plane,
the curvature is -1. These are called hyperbolic free manifolds. What they are equivalent to is saying that the universal cover is actually the hyperbolic three-dimensional space. For those who are, I mean, it's essentially for those in string theory, it's ADS3 but with rotated. So H3. So that's the those are the pieces that were conjectured to be generic. Yeah, it was a very bold conjecture by Thurston. He proved a lot of free manifolds do admit hyperbolic metrics. He conjectured that generically everyone does. So this was the geometrization conjecture. After cutting along essential tori, either you have cipher fiber pieces or a product of torus that is 0, 1, or the generic case is that they're hyperbolic pieces. So in particular, if you cannot decompose along any tori, the conjecture was that they would be hyperbolic. So this was conjectured by Thurston and proven by Aaron. So really, the hardest part of this whole talk is really concentrated in this theorem, and that also in the condition 2. You take a generic piece without where you cannot decompose. So basically, you start off with something which is already prime. You also note that it does not contain any tori, which means that you cannot decompose it further. So then Thurston's conjecture would say that such objects, such free manifolds are necessarily hyperbolic. And that was the hardest part of the geometrization conjecture. It's proven by Feldman. So now let's assume, so this is really the content of the geometrization conjecture that's relevant to this particular talk. Okay, fine. So we've been trying to simplify our life. We started with three manifolds, arbitrary closed three manifolds. When we decompose them along spheres to get prime three manifolds. Then we started with prime three manifolds and we started decomposing them along tori as far as possible. And then the pieces that we were left with, either they are well understood, either they are product of torus with 0, 1, or they're cipher fibered, or, and the generic case was that they are hyperbolic. Things which are locally like torus cross 0, 1, they're relatively easy to understand. Things which are cipher fibered are also easy to understand. But what about hyperbolic objects? These are generic objects, of course, they are relatively complicated. So once you can decompose into pieces, the topological classification then reduces by some little bit of work, not much, really reduces to the classification of hyperbolic three manifolds. So from starting off with arbitrary, go to prime, then do torus decomposition, and then finally the generic piece are hyperbolic three manifolds. And so our original problem, see, this is the best possible metric theorem. The geometrization theorem basically says that you can decompose into objects which do admit canonical metrics, and of these, the generic ones admit hyperbolic metrics, very special constant curvature -1 metrics. So the geometrization theorem really solves this question that we had posed in the previous slide of find best possible metrics. So the geometrization conjecture does that. It finds the best possible metric and tells you that the generic case is hyperbolic. And so the topological classification problem reduces to the classification of three manifolds, reduces to the classification of hyperbolic three manifolds. Three manifolds which admit metrics of constant negative curvature, constant curvature -1. So how are we going to do this? Okay, this moment I think my headphone has run out.
Yeah. Am I still audible?
Yes.
Yeah. Okay, great. Terrific. So now we have reduced this classification problem to the classification of hyperbolic three manifolds. And this is the final step. What happens? This is a theorem which was proven by Mostow in the 60s, and then so essentially you can take complete finite volume hyperbolic manifolds. So the thing is, once you've cut along tori and you put a complete hyperbolic metric there, then the torus goes off to infinity. I mean, it's not a compact object,
the torus it sits on the boundary, but you want to put a complete metric, so you have to push the torus off to infinity. It turns out that these are finite volume, but not compact. So, but if you don't have tori, that means they're already compact. So what Mostow and Prasad did, they proved that if you have two complete finite volume hyperbolic three manifolds, yeah, it's actually true for all dimensions greater than or equal to 3, then just this soft fundamental group information, just suppose that the fundamental groups are isomorphic. It's very soft topological information. Then just this soft topological information gives you complete geometric information. Such an isomorphism is induced by an isometry, which means suppose you have these guys which are complete hyperbolic metrics, and you are told that they have an isomorphism of fundamental groups, then that isomorphism of fundamental groups really comes from an isometry, a distance preserving map. So it's a this is called a rigidity statement. Essentially, soft topological information gives you hard geometric information. So this is the Mostow-Prasad rigidity theorem, and basically says that three manifolds, their metrics, hyperbolic metrics, are determined just by this information of the fundamental group. So which means that the classification of geometric structures really reduces to this classification of fundamental groups. So remember that in the previous discussion, in the previous lecture, first hour, we had said that four-dimensional manifolds cannot be classified because their fundamental groups are not classifiable. What this rigidity theorem is saying is that, well, if you can classify the fundamental groups, then you will be able to classify the manifolds themselves. Okay. And is somebody drawing on this? Yeah. Okay. So here is the thing. So it really remains to classify three manifolds, and just the fundamental group information is good enough. So the question of classifying, so after geometrization, what happens? We have reduced from prime to torus prime to hyperbolic. And then now we are asking, well, if you have two such hyperbolic three manifolds and you are given their fundamental groups, does there exist an algorithm which says that these groups are isomorphic or not? Right? So some problem which started off by a soft classification problem up to homeomorphism of all three manifolds now has become reduced because of this rigidity theorem just to a classification problem for fundamental groups. And this is the last bit. So we have reduced the classification to the classification. So this theorem reduces hyperbolic three manifolds to fundamental groups. And here is a theorem. The answer is, to this restricted problem, if you had arbitrary finitely presented fundamental groups, we've already seen that the classification problem is not solvable. Yeah, we saw that in the previous 1 hour. So we took our two-dimensional complex, embedded it in R5, took a thickened neighborhood and took the boundary, and we got all these four-dimensional manifolds, but a classification of all finitely presented groups is basically equivalent to the halting problem. So that problem is not solvable. But now we have a restricted class. We are looking at not arbitrary groups, not arbitrary finitely presented groups, but finitely presented groups that do appear as fundamental groups of closed hyperbolic three manifolds or finite volume complete hyperbolic three manifolds. And this theorem says that fortunately an algorithm exists. So if an oracle in the computer science language tells you that these groups that you are interested in, they are not arbitrary, but they belong to this very special class of fundamental groups of closed hyperbolic manifolds, the theorem says that this classification problem is solvable. There exists an algorithm which takes as input the fundamental groups of two potentially different finite volume hyperbolic three manifolds, M and N. And what is the output? The output says that these fundamental groups are the same. or they are different. Once it outputs that the fundamental groups are different, then you automatically the manifolds have to be different because they cannot be isometric. Isometry is a much tougher restriction. But if on the other hand, the algorithm spits out the answer yes, pi1m is equal to pi1n as groups, then Morster-Prasad rigidity kicks in and tells you that the manifolds are not just fundamental groups same, they are isometric as hyperbolic three manifolds. So which means, so this algorithm solves the last step, and with this, so who are the people who proved this? This isomorphism problem was proved by Salil Salah when M is closed, compact, and by Dahmani and Groves when M is non-compact, which means basically the finite volume non-compact case. So once you have this, the isomorphism problem is solved. Hence, the homomorphism problem for hyperbolic manifolds is solved. And then you rewind, go back to your torus decomposition, go back to your sphere decomposition. So classification of three manifolds can be done in principle. So that's the end of it. And thank you very much. Thank you very much for your patience.